As announced the last time, today I will talk about conjugate points. If Mg is a Riemannian manifold, and gamma is a geodesic, with gamma A equal P and Q equal gamma B for some A, B in I, then we say that P and Q are conjugate along gamma if there exists a Jacobi field along gamma vanishing at A and B. The first thing I want to do is to make some observation which justify why the first result I will present today is about the relation existing between critical points of the exponential map and zeros of Jacobi fields. We know that the restricted exponential map, denoted by this symbol, is defined on a subset of the tangent space at P, denoted by EP, and since this is smooth between manifolds of the same dimension, then we can use the inverse function theorem to prove that it is a local diffeomorphism in a neighborhood of each of its regular points. This sentence means that this map is a local diffeomorphism in a neighborhood of points V of TPM such that the differential of the exponential map restricted at P evaluated at V is surjective, and this implies that it is invertible. So our goal, our first goal is to identify points where this is not true, and the first thing we can say is that V equals 0 is a regular point, because we know that differential of the restricted exponential map at 0, this is the identity. So this point is okay. But there are maybe some points of EP where the differential is not surjective. For example, let's consider the special case where M is the sphere or radius R. We know that if we choose a point P of the sphere, then all geodesics meet at the antipodal point. Sorry, my picture is not like this. And we know that this point is located at distance pi r along each geodesic. So the exponential map is a diffeomorphism on the ball centered at 0 and the radius pi r, but every point of the boundary is a critical point. And we have seen recently that proposition 10.12 says that the Jacobi fields for the sphere of radius R have this form, where SCT is R sinus of T over R, and ET is a parallel unit normal vector field along a geodesic. And these Jacobi fields have their first zero exactly at distance pi r, which is the distance between p and minus p. Secondly, we have also found a formula for the representation in normal coordinates of Jacobi fields. This formula says that Jt looks like this. So this formula says that a Jacobi field does not vanish where on the set where this formula holds true. This means in a normal neighborhood. So this makes us think that there could be a relation between the critical points of the exponential map and the zeros, the first zeros of Jacobi fields. So what I want the result I want to present now is the following. Suppose that P is a point of Riemannian manifold. V is a vector in EP, and let gamma be the geodesic gamma V, the geodesic segment starting at P with initial velocity vector V. And let Q to be gamma 1 equal exp P V. Then we have that V is a critical point of the restricted exponential map if and only if Q is conjugate to P along gamma. Let's prove this result. So suppose that V is a critical point, and then we have that there exists W in TV TPM, which can be identified with TPM such that the differential of the exponential map evaluated at W is equal to 0. What we have to do now is to prove that Q is a conjugate point, and we do this considering a variation of gamma, precisely the variation gamma S T equal X P T V plus S W, and let JT be its variation field. Then let's compute J1, and let's show that this is 0. This proves that Q is conjugate to P because Q is gamma 1, and J satisfies not only this identity but also J0 equals 0. This is immediate from formula. So what is J1? This is ds at S equals 0 of X P V plus SW, and this is just the differential of the exponential map at W, and this is 0 by hypothesis. Now let's prove the converse. So Q is conjugate to P. Then there exists non-trivial Jacobi fields J such that J at 0 is equal to J at 1 equal 1. Lemma 10.9 can be used to prove that such a Jacobi field is a variation field of the variation gamma st equal exponential map at P TV plus SW, where W is dt j at 0, and then in order to prove that we have a critical point of the exponential map, we just reuse this computation here and prove that this is true. But by hypothesis, this is 0. So V is a critical point for the exponential map. And this is the end of the proof. Now we are ready to present the fundamental result which allows us to show that geodesic is not minimizing past a conjugate point, and this result is known as a second variation formula, and says what follows. Let gamma unit be a unit speed geodesic segment gamma capital gamma be a proper variation of gamma. Please note that here J is an interval and not a Jacobi field, and V its variation field. Then we have that the second variation of the length of gamma s is given by this formula. Where V orthogonal is the normal component of V. Before proving it, I want to say that it is not surprising that this formula involves only V orthogonal. And the reason is that the tangential component of V contributes only to reparametrization of the curve gamma, and the length, we know that it is a invariant under change of parameterization. So when we take a derivative of it, we expect not to see any contribution of V tangential. And this is what happens here. Okay, so we set capital T to be delta T gamma S equal delta S gamma, and we assume that A0, A1, AK, this is an admissible partition of gamma. So let's consider the restriction of gamma at J times AI minus 1 AI. We know that inside this rectangle J is smooth, and we can take its derivative. So we already computed the first derivative of the length of gamma S restricted to a I minus 1 AI, and we obtain the integral from AI minus 1 to AI, of this quotient. So what we have to do is to differentiate one more time, and I don't need this bracket, sorry. And here we get three terms that I will not write down. The first one involves ds dt ds, sorry, dt ds dts. The second dts dst, and the third one is the term that you get when you differentiate the denominator. The term containing ds dt st can be written in another way using the formula which says ds dt v minus dt ds v equal r delta S gamma, delta T gamma, V, where V is a smooth vector field along the variation gamma. In this case, we get the integral from AI minus 1 to AI of dt ds s plus this term r s t s comma t divided by the length of t. I write this denominator as length of t. Then I copy the term involving dts dst, so no change. dt s, no, actually let's skip a step. I should write here dst, but I can use the symmetry lemma, and instead of writing this, I can write dts divided by the length of t, and then there is the apparently more complicated term involving the derivative of the denominator, and I should write I don't want to waste time, but maybe it is clearer if I write, I should write minus 1 over 2 times dt s t times 2 dst t over the inner product of t with itself power 3 over 2. But you can use again the symmetry lemma, and you can write this as dts, then you get the square of dtst, inner product, divided by the length of t power 3. So I erase and I write minus dts t squared over length of t power 3. So now we evaluate at s equals 0. The first consequence is that the length of t is 1, and the formula becomes d square ds square at s equals 0 of Lg of gamma s restricted to this subinterval dt ds s comma t minus Riemann tensor evaluated at s t ts plus dts square minus dts t square dt at s equals 0. Now I can erase this part of the blackboard. And let's observe that s equals 0 implies also that dt capital T reduces to dt gamma prime, and this is 0 because gamma is a geodesic. Then let's see what happens at this term. This term here can be written as the derivative of the inner product dss and t. The reason why this is equal to this is that there is no term involving dt capital T because it's equal to 0. But this is easily seen to be equal to this. Now observe that capital S S T, this is 0 for all S at T equal A0 equal A and T equal AK equal B, because we are working with a proper variation. So this means that all the gamma S curves have the same endpoints, and consequently the derivative of gamma with respect to S, which is exactly capital S, it is 0 at t equal A and t equal B. Let's observe that along the boundaries of the subintervals, where the variation is smooth, ds S is ds, this is just definition. This depends only on the values of gamma when t equal AI, and it is smooth up to the line t equal AI from both sides. These remarks implies that dss is continuous and this means that when we make a sum on I of terms like this, the boundary contribution cancel out. As a result, we get that d2ds square of Lg gamma s, this is just the integral from a to b of dts square minus dts t square minus rm s t t s dt at s equals 0. And this is equal to the integral from a to b of dtv square minus dtv gamma prime square minus rm v gamma prime v dt. So what I did is just the replacement of s by 0, and you get that instead of s you write v, because v is the variation field of our variation. Now we observe that v can be written as v orthogonal plus v tangential, and we have that v tangential is v gamma prime inner product times gamma prime instead v orthogonal is v minus v tangential. Now let's show that v tangential does not give any contribution to this integral. So let's observe that dt v orthogonal, this is equal to dt v gamma prime. I took the covariant derivative of this, and you get only one term because dt gamma prime is 0. So you get only this term here. But if you think a moment, this is just dt v tangential and dt v orthogonal. This is equal to dt v orthogonal then what is dtv square? It appears here. This is dtv tangential square plus dtv orthogonal square and this is dtv gamma prime square plus dtv orthogonal square the consequence of this formula is that dtv square minus this term, which appears exactly here, is given by dtv orthogonal square. What about this term? You use the fact that Rm gamma prime dot dot is 0 as well as Rn dot dot gamma prime and this is what you get if here you replace v equal v orthogonal plus v tangential. Precisely when you replace v tangential by this formula, you will get Rm of gamma prime, and this is 0 because of this identity. And when you replace v tangential here, you will get Rm of something gamma prime, and this is 0 because of this identity. So this says that instead of writing Riemann tensor evaluated at v gamma prime v, we can write just v orthogonal instead of v. And this is the end of the proof. So we proved that the second derivative of the length of gamma s involves only the normal component of the variation field, of its variation field. So in the sequel we will consider only normal variations, that is variations such that their variation field is normal along gamma. The next step is to introduce the index form of a geodesic segment gamma precisely it's a symmetric bilinear form acting on the space of normal vector fields along gamma, and it is given by the integral from A to B of dtv dtw minus rm v gamma prime w dt, where v w are normal vector fields along gamma. Using previous theorem, it is possible to prove this corollary. Suppose that gamma is a geodesic having unit speed suppose that capital gamma is a proper normal variation and V is its variation field. Then it is clear that d square ds square at s equals 0 of Lg gamma s, this is IVV. If you put V equal W, you get dtv square with V normal minus Rm V gamma prime V. So the two formulas coincide. And if gamma is minimizing, then IVV non-negative for every proper normal vector field along gamma. it is possible to find out another expression for the index form, and this is interesting because this expression involves the Jacobi equation. So we have this proposition which says that for every piecewise smooth normal vector fields VW along gamma, then IVW is given by this formula. Where A0, A1, A2, AK is an admissible partition for V and W. This makes sense because they are piecewise smooth, and delta I dt V, this is the jump of dtv at t equal AI. How to prove this formula? As we did before at least 3 times, we look at the behavior where of the maps, in this case vector fields, are smooth. So we look at V restricted to AI minus 1 AI and W restricted to AI minus 1 AI. And then makes sense to take this derivative And let's observe the following fact. This is the term which appears in the initial formula for the index form. This is the term we want. It is here. So what we have to do is to use the fundamental theorem of calculus. And we integrate this inner product on the subinterval ai minus 1 ai. And clearly we get minus ai minus 1 ai of dt square vw dt, which is exactly this term, and this also explains why we have a minus sign here. And what about these terms? I will erase this part. They comes from the term I'm going to write now. This is dtv w evaluated at ai minus 1 ai. And we have only to now sum up sum over I, and using the fact that W is continuous at t equal AI. And clearly you get these two terms. This is the term that you get when AI is B and aj minus 1 for a different value of I, so I use j, is equal to A. That is A0. As an exercise, you can try to prove this corollary. The idea of the proof is that in this formula you have the left-hand side of the Jacobi equation. So if gamma is a geodesic segment, V is a proper normal piecewise smooth vector field along gamma then IVW is 0 for every proper normal piecewise smooth vector field W along gamma if and only if V is a Jacobi field. One direction is immediate. What is interesting is the other one. So if V is a Jacobi field, then this is 0. What is interesting is to see that IVW 0 implies that V is a Jacobi field. Try to find the idea. And now I will present the statement of the theorem I will prove next time. So definition: given a geodesic segment gamma defined on AC with values in M, we say that gamma has a conjugate point if there is some B in AC open on the left and closed on the right, such that gamma B is conjugate to gamma A along gamma, and we say that gamma has an interior conjugate point if there is such a B in AC. So the difference is that this interval is open, and this interval is open on the left and closed on the right. Next time I will prove that this theorem holds true if P and Q are points of a Riemannian manifold. Then if gamma is a unit speed geodesic segment from P to Q that has an interior conjugate point, then there exists a proper normal vector field X along gamma such that the index form evaluated at xx is negative. Therefore, gamma is not minimizing. Okay, let's stop here. Thank you for watching.